Hello.
Our next speaker is Yuxiang, and he's giving the talk remotely. But as you can see, another author is here in person. Let's give it a minute, just in case someone wants to step in to synchronize the sessions. Can we hear you, Yuxiang?
Hello, can you hear me? I can hear you.
Yes, we can hear you.
Sure.
All right, I think you can go ahead and start. So, sorry.
Okay.
Yuxiang will tell us about SimuQ, a framework for programming quantum Hamiltonian simulations with analog compilation. Go ahead.
Yes, thank you. Thank you for the introduction. Hello, everyone. In this talk, I will present SimuQ, a framework for Hamiltonian-oriented quantum computing. I'm Yuxiang Peng from the University of Maryland, and I'm on the academic job market. So reach out to me if you are interested in my research. I cannot travel to London because of visa issues, but Professor Xiaodi is there in person for the session. You can feel free to discuss the research from our group with him. Many resources about SimuQ are available online, including the GitHub code and the tutorials and the project website accessible through all these barcodes. Let's start with the basic knowledge of quantum Hamiltonian simulation, in case some of you are not familiar with it. The evolution of a quantum system obeys Schrödinger equation, which is an ordinary differential equation. A quantum system is governed by a Hamiltonian, HT here, essentially is a Hermitian matrix function changing over time. We have a minimal example here. While two qubits are in a system, initially the state is beside naught, a four-dimensional complex vector. The Hamiltonian HT here is Z1 and Z2, which is the diagonal matrix. The quantum Hamiltonian simulation problem asks for the state after an evolution time t. In general, the Hamiltonian is exponentially large with respect to the number of sites or qubits in a system. Hence, it is very hard to compute for classical computers. 40 years ago, the famous Richard Feynman proposed to emulate a quantum system with another precisely controlled quantum system to avoid the curse of exponential dimensionality. An illustrative example is the dynamics of an electronic system of an atom, which is very hard to control in physics. Researchers now choose to manufacture superconducting chips to simulate the Hamiltonian system, which describes the dynamics of the electrons. However, there is a lack for software tools to help with such computing tasks. This is where SimuQ helps with the situation. SimuQ is a framework for users to program and simulate Hamiltonian systems. SimuQ employs an analog compilation scheme to deploy the program and the simulation tasks on analog quantum devices. Now, you may have observed that this is a work that heavily leans towards quantum computing. Actually, the most frequent question we faced during the reviewing process was, what does your paper do with programming languages at all? I would like to use this opportunity to share our view on how programming languages and other domains co-develop. The main theme of programming language research is to adapt tools like formal verification to help with the control of devices in domains like quantum computing or parallel computing. In these domains, new models, applications, and user communities emerge and grow over time. The element connecting programming languages and the specific domains is abstraction, which is basically the formal model for people to think, program, and control devices, and eventually compute with the devices. Abstraction connects the applications and the underlying devices. A good abstraction should be flexible enough for various important applications and efficiently implementable on the hardware. Our role model is actually the Fortran language, whose major contributions include the capture of the high-level description of floating point systems, which used as the main abstraction. The floating point system is realizable by the IBM 700 series devices with very small overhead. This abstraction is very convenient for applications from the scientific computing community to use. From Fortran's history, we can observe a bidirectional stimulus coming from a good abstraction in the co-development of programming languages and other domains. First, the abstraction and language is the development of applications on actual devices. Second, they can also motivate new solutions to broader applications. We mimic the essence of the Fortran design and choose the abstraction of Hamiltonian systems in SimuQ for quantum computing. This is very native to existing analog quantum simulators, which are essentially precisely controlled quantum systems. One very interesting fact I want to share is that SimuQ may be the first paper in the history of POPL and PLDI that actually leverages real quantum devices to tackle practical problems. Then I want to move to a more historic view. Along with the hardware development, abstractions and programming languages will change over time, and this shift is highly dependent on the evolution of the devices. For example, Fortran was designed in the 1950s when the IBM 700 series came out with hardware floating point implementation. Simula was designed in the 1960s when the UNIVAC 1100 series came out, which brings data abstraction to solve system simulation problems. And around 2000, Brook proposed the data parallelism as an abstraction, which was later turned into CUDA and was widely applied on NVIDIA GPUs for gaming and machine learning applications. With each of these programming languages designed for the devices, there was prosperous research around the practical solutions to important application problems. This exhibits how programming languages and classical computing domains were co-developed in history. Now we turn our view back to quantum computing and put SimuQ into such a timeline. Due to the development history of quantum computing, the quantum programming language research is somewhat reversed in order. Prior work links towards circuit abstractions or even higher level abstractions, because those are how the theory of quantum computing developed. This is actually deviated from how the actual devices are manufactured and functioning. We want to emphasize that current quantum devices are in the early practical stage if we employ the Hamiltonian system as an abstraction because of the low overhead to implement them on existing devices. Meanwhile, there is a huge underexplored space for applications. We believe that now is a time for quantum programming languages research to focus on the practical problems and real quantum devices. For example, the new abstraction and programming languages in SimuQ have already motivated several new algorithms for new and important applications. A follow-up work we just released this week called QuEra is a software for nonlinear optimization with a Hamiltonian-based quantum algorithm. The practical performance of QuEra often beats existing open-source solvers for non-convex problems. We hope that this development, which is based on SimuQ, can further expand the user community of quantum computing. We believe such co-development of programming languages and quantum computing is very promising in advancing both fields at the same time. SimuQ relies on the concept of Hamiltonian-oriented quantum computing, which is a terminology we borrowed from, obviously, object-oriented programming. Conventionally, researchers follow circuit-oriented quantum computing paradigm, while quantum algorithms are represented by quantum circuits. These circuits are compiled into elementary quantum gates, and hardware manufacturers try to realize these elementary quantum gates on their devices. Hamiltonian-oriented quantum computing directly describes quantum algorithms with Hamiltonian systems and simulates the Hamiltonians on quantum devices, including analog quantum simulators, of course. The benefit of using Hamiltonian as a direct abstraction is that it can avoid multiple layers of abstractions that cause huge overhead in each of them. Unlike circuit-oriented software stacks, where many tools have been developed already, there are few software tools to help with Hamiltonian-oriented quantum computing. This mismatch motivates us to propose SimuQ, in which you can directly program the quantum Hamiltonian simulation system to represent Hamiltonian-based algorithms. Through an analog compilation scheme, SimuQ can generate executable pulses and send them to multiple platforms of analog quantum simulators for execution. For example, after programming the Hamiltonian, you can ask SimuQ to generate a quickly pulse program for IBM's superconducting system to execute. Alternatively, SimuQ can also generate an atom position arrangement and laser pulse schedules for QuEra's variable atom arrays. You may even generate a quantum circuit for IonQ's trapped ion systems because they only accept circuit-based inputs. Short speaking, SimuQ is a software framework designed for Hamiltonian-oriented quantum computing. Lying at the core of SimuQ is the abstraction for analog quantum simulators. This abstraction is actually non-trivial. The difficulty comes from the fact that different quantum devices are vastly different in their physics and technologies. So we seek unifying description of these analog simulators. Here is an illustration of how a quantum device is actually controlled. Experimental physicists send classical pulse signals in the form of microwave or lasers, which interacts with the quantum system and generates an effect described by a Hamiltonian. Then the Hamiltonian governing the evolution is a summation of all these Hamiltonians induced by the physical pulses. We abstract these concepts into what we call abstract analog instruction sets, abbreviated as AAIS. Each instruction execution generates a partial Hamiltonian on the device, mathematically described by a parameterized Hamiltonian. Then an instruction schedule shows which instructions are executed at each time. For example, at time t in the schedule here, eta 1 and eta 2 are executed with parameters 1, effectively generating a Hamiltonian z1x2 plus z2x3 at time t on the device. The abstraction of AAIS leads us to the language design and compiler implementation in the SimuQ. Here's the overall framework of SimuQ. For the details of all these components, please refer to our paper, and we only briefly introduce them here because of the time. Currently, we design and implement several AAIS on our own. In ideal cases, we hope the hardware developers can design AAIS for their specific devices and program them in the AAIS Specification Language, which we have implemented in Python. Here we have an example code snippet for an AAIS SL program. For front-end users, they can program the target quantum systems they want to simulate in Hamiltonian Modeling Language. A short example is shown here. You can see that you only need to write a few lines of code to program a Hamiltonian system. Then the AAIS and quantum systems are sent into the SimuQ compiler to generate pulse schedules and send them to quantum devices to be actually executed. Here we briefly give a glance at SimuQ's solver-based compiler. We propose several intermediate representations to decompose the compilation process into several natural steps. The most important component here is the Hamiltonian synthesizer, which determines the set of instructions and their parameters to synthesize the desired Hamiltonian. We modeled this problem as a mixed integer equation system and crafted a least square-based solver to obtain a solution. Additionally, we have a semantics preservation theorem stated in our papers illustrating the correctness of SimuQ's compiler design. For more details, please refer to the paper. Moreover, for specific devices like IonQ or D-Wave devices, we recently built customized solvers to speed up the compilation process. SimuQ is a platform for interdisciplinary collaboration to advance applications on real quantum devices, and we have already connected to many research groups to expand the usage of SimuQ and extend its functionality. We have worked with Professor Lei Fan at the University of Houston from the industrial engineering and operational research communities to develop QSD-Ops, which we have introduced before. It's a software for nonlinear optimization that often beats classical solvers on non-convex problems. We plan to integrate this software into industrial software like MATLAB and Mathematica to provide a quantum solution for users in other domains. We are also working with Professor Ling Ling, a mathematician at the University of California, Berkeley, to test their Hamiltonian-based quantum algorithms. A possible extension of SimuQ integrating automatic differentiation is also planned to consider parameterized quantum systems and the optimization of them. The theory of such automatic differentiation is presented in our paper in EURIPS. We are collaborating with physicists to develop domain-specific languages for quantum chemistry and high-energy physics to deploy pulse-based variational algorithms for the problems they care. On the programming language and system side, we are managing to formally verify SimuQ and optimize its compiler. For the low-level machine-related research, we are working with Professor Gregory Quiros from Johns Hopkins University Applied Physics Lab to test and integrate dynamical decoupling technology and integrate it into SimuQ. We are also adding support for D-Wave and regated devices and further collaborating with experimental physicists to support laboratory devices. SimuQ is an open source project, and we welcome more collaborations across the community of computer science and quantum computing to further expand this usage. Now we go to a quick recap of this talk. SimuQ, as we have talked, is an end-to-end framework for Hamiltonian-oriented quantum computing. We propose new and novel abstractions, languages, and compilers to support this framework. It helps harness the power of real quantum devices for practical applications. And thanks for the listening. Here are the links to barcodes to the links to the online resources, and any questions are welcome.
And we have a few minutes for questions.
Hey, nice talk. I come from a trapped ion compilation job, so I'm targeted from that direction. But do you think it's worth investing in these kind of pulse level compilation techniques if like the longer goal is to get to fault tolerant kind of devices that are like getting gate level programs?
Well, as we have shown in the timeline, let me turn the slides back. So the most optimistic estimation for like actual fault tolerance device to come out is around like 20 or 30 years later. For the next 10 years, we believe that the most applications will still be around the pulse level compilation. And we believe that 10 years is a long span for a programming language to survive. So I think, yes, it's worthwhile for us to develop in the pulse level compilation techniques.
Okay, thanks. Yeah, I think of it as breaking abstraction, but I think of the short term. That makes sense. And then the second question was, did you have any advantage with this approach for IonQ's devices since you were like going back to gate-based circuits?
Well, I mean, the core problem for IonQ devices is that they do not provide pulse level API access for us, at least out of their companies. So we can collaborate with other trapped ion experiment groups to consider any like experimental proposals. But from what we have demonstrated with the QuEra and other platforms, there are definitely benefits from breaking the abstractions into pulse levels.
Okay, thanks.
So this is similar to the question before, but I noticed you're targeting a very broad range of different, fundamentally different architectures, and you're also, targeting them at very different levels of abstraction. As in IonQ, you're using gates, and in others, you're using very low-level pulses. Would you say that there is an architecture and a level of abstraction among current devices that is most amenable to running programs in SimuQ? And could you say a little bit about how they compare?
Well, the overall abstraction we use is for the AAIS, which is the description at the Hamiltonian level. Actually, for trapped ion devices, we can also do this. But the drawback, of course, as I mentioned, is that IonQ did not provide APIs for like the Hamiltonian level descriptions and controls. So at least for IBM device and the QuEra device, we actually program them at the Hamiltonian level. And the implementation actually involves quantum technologies that use how to use a pulse to construct Hamiltonians. But the general tune is that any quantum system can be described by the Hamiltonian level description, and every physical pulse actually have a direct correspondence in the Hamiltonian level. And we think that this is a very native way to describe what is actually happening on a quantum device. So we think, yes, we should have investigate more API development and control development in this direction.
Thank you for great talk. The proposed language is, I think the proposed language can describe the Hamiltonian quantum devices directly, right? This is right. Is this right?
Do you mean that we can describe the Hamiltonian of the quantum device?
Yes. So your languages can manipulate directly the Hamiltonian of the quantum devices.
Yes, in principle, yes.
Yeah, so I'm curious about this. We write some quantum simulation programs in this program manually, or we can use other more high-level quantum programs, and then we transpose them into these your languages.
Yes, of course.
Okay. So the, why my intention is can we write can we understand the quantum meanings of the quantum programs more easier than the quantum circuit model?
Well, it's quite possible. I mean, at least it's very native to what is happening on the actual devices.
Mm-hmm.
And as you have said before, we have an example showing that we can develop a higher level languages and compile it to SimuQ and use SimuQ to compile it to actual devices. And it's the QuEra opt we have advertised a little bit before.
Okay.
Right. Sorry, I think we have to take the rest of the discussion offline.
Okay, thank you.
Let's thank the speaker again.
Yeah, thank you.
Thank you.